Let's take a look at the properties of waves. All right, we're going to represent waves in a similar way to this one here. We've got a wave that goes up and down, kind of vibrates back and forth. All waves can be represented in this way. Even longitudinal waves we can represent in this form. It doesn't look obvious about how we do that, but we can take a longitudinal wave where the displacement is back and forth and the wave travels this way, and we can represent it in this form here. All right, so we're going to talk about the amplitude of the wave. The amplitude of the wave is the size of the displacement from the rest state. So the amplitude is the size of the displacement from the rest state. All right, when we graphically represent a wave, right, we're going to start with a wave here, and I'm going to draw it up like this, down here. That's going to be one complete cycle of the wave right there. So I've got one complete cycle. There's our wave. And it goes through one cycle. This is the rest state right here. Okay, so that's kind of its natural state. And the wave vibrates up and vibrates down. The amplitude is the size of the displacement from the rest state. So this right here is our amplitude. This right here is our amplitude. These two distances will generally, in our waves, will be the same. So our amplitude is there and right there. Now our amplitude can be measured in centimeters, millimeters, or some other units, depending on how the wave is represented. All right, so that's the amplitude. In a wave, the energy of a wave is proportional to its amplitude. Proportional to its amplitude. All right, so as amplitude increases, then our energy increases. Now, when we can think about this in sound waves, louder sound waves have bigger amplitudes. And if you've ever watched really high-powered subwoofers go, you can see the speaker cones move in and out like a few centimeters, producing very loud sound waves with very high amplitudes. Right, so the wavelength. The wavelength, we give a special symbol. It's kind of this symbol here. This is called lambda. And this is the symbol for wavelength. Wavelengths we usually measure in, well, a lot of times we measure them in distance. A wavelength is the distance between 2 points that are in phase. So these 2 points are in the same kind of place of the wave. Right, so if we sketch out a wave again. Goes up, down, up, down. All right, so right here is our wave. There's our rest state. So 2 points that are in phase. Right here's one point, right here's another point. The wavelength is this distance. This is lambda. I can choose multiple other points to measure. This point right here is in phase with this point right here. This distance here is lambda. These 2 points are both in phase. They're both at the same height, and they're both on the downward swing. This point and this point are not in phase. All right, now, the speed of a wave is simply how fast the wave travels. How fast the wave travels. We usually measure this in meters per second, but it could be in kilometers per hour. So water waves have variable speeds. Water waves have variable speed. Light waves travel at 300,000 kilometers per second in a vacuum. Light waves travel slower in glass and water. So they can be affected by glass, water, or anything they travel through. They can slow light down. Compression waves, like sound waves, travel different speeds in different mediums. In the air, sound travels a certain speed. On the railroad track, in steel, sound travels a different speed. In water, sound travels again a different speed. There's a formula for velocity that you should know, and it simply looks like this. The velocity of the wave is equal to its wavelength times its frequency. We're going to talk about frequency pretty soon. Wavelength is right up there, that's our lambda, and frequency is coming up. So phase. We already talked a little bit about 2 points that are in phase. So let's draw a wave again. Now you can see how you can see through. Okay, so we're going to have to draw 2 wave. Okay, so right here's our rest line. So 2 points are in phase. If they are on matching parts of the wave. Okay, so this point right here is in phase with this point right here. These 2 points are considered in phase because they're on matching parts. They're on matching parts of the wave, right? They're at the same height on this downward slope. Now we can say they're 360 degrees in phase. There's a reason for that. We say that they're 360 degrees in phase. This point right here and this point are not in phase. They're out of phase. This is halfway across the wave. Halfway across the wave is 180 degrees. So these are 180 degrees out of phase. They're kind of opposite points. 360 degrees in phase, matching. 180 degrees out of phase are at opposite points. So you look at these 2 points right here. These are 360 degrees in phase. This point and this point up here are 180 degrees out of phase. They're at opposite points. Right? These two are at opposite points. They're both at the rest state, but this guy's at the rest state going down. This guy's on the rest state going up. So 180 degrees out of phase. These 2 points are 360 degrees in phase because they're on the matching part of the wave. These 2 points would be 360 degrees in phase. These 2 points right here would be 360 degrees in phase. Okay, you could also have 90 degrees out of phase. 90 degrees out of phase would be like here and here. A quarter of the way through the wave would be 90 degrees out of phase. So 360 degrees is like one whole wave away. 180 degrees is half of a wave away. 90 degrees would be a quarter of the wave away. What is the period of a wave? The period of a wave is the length of time it takes for a wave to complete one cycle. So one whole wavelength. And we've got a little formula for this, but it's not on your formula sheet. The period is equal to 1 over the frequency. It's inversely proportional to the frequency. You'll find that in your textbook when you do your textbook readings. Right, the frequency of a wave. The frequency of a wave is how many complete cycles of the wave occur in 1 second. So how many complete cycles of the wave? So a complete cycle is from here to here. Goes to one, that displaces to one side, then displaces to the other side, then back to rest state. That's one cycle. So how many complete cycles of the wave occur in 1 second? This is measured in hertz. Hertz. Okay, so 1 hertz is equal to 1 complete cycle per second. Now, for human hearing, the lowest frequency we can hear is usually about 20 hertz. When you see a subwoofer going 20 hertz, you can watch the cone move in and out, in and out, in and out 20 times every second. That's as low as we can hear. So the cone would start at the rest stop, go in, out, back to the rest stop. We do that 20 times per cycle, the cone of the speaker would. And young people with good hearing can sometimes go all the way up to 20,000 hertz. That means that speaker goes from the rest space, in, out, back. It does that 20,000 times every second. That's a very high-pitched sound. Usually only young people can hear it. Old people like me cannot. I max out at about 15,000 hertz, I think. We'll get some tone generators and we'll listen to it. Crest. So when we're looking at a wave, we're just going to draw one for both of these. Here's our wave, back and forth. Up here is a crest. It's the maximum displacement in one direction, and the trough is the minimum displacement in the other direction. In a sound wave, the crest is our high pressure area, and a trough would be a low pressure area. Because the sound wave is a compression wave, and we have areas of high pressure and low pressure, or areas of compression and rarefaction. And the crest would be the area of compression, the trough would be the area of rarefaction. All right, so at the end of this, there are some readings to do and some questions. And we'll take a look at those questions in another video. And on Desmos, if you graph y equals sine x and y equals cos x, you can take a look at what they look like. Because it's always nice to have a mathematical model for our waves. All right, so thank you for watching. Do your readings, do your practice questions so you know what's going on. And we'll move on to the next section.